let's look at beta decay. So these are the two beta decay reactions. Notice that there's another little particle here. This is a neutrino. Yes? Okay. And the reason that there's a neutrino there, and these guys were confirmed in like 1956 or something like that. The reason why these particles were originally hypothesized to exist is the following. If we look at the energy of this, as you go this side minus this side, the energy released was not nearly given to these electrons, these beta particles, right? They didn't possess nearly that much energy. In fact, their energy spectrum is actually continuous. It's sort of like they're given an energy that is sort of kind of like around a certain amount, but not exactly a certain amount, right? And so either, and this is not like short term, we're talking long term, like by seconds later as they're detected by some detector or something like that, right? They didn't have this energy, they don't have it, they never will have it. We're not talking quantum non-conservation of energy like Heisenberg uncertainty. We're talking like long-term stuff here. So you either were going to reject conservation of energy, or you were going to hypothesize that some particle that was very hard to detect existed. Yes? Yeah. Usually we're skeptical of these sort of explanations, but the alternative, that energy is not conserved in the long term, was far more repulsive, right? The second thing you need to know, and IBII says that you really should know this, right? Remember that a beta minus is a regular electron, okay? The neutrino that is released when a regular electron is released, okay? And remember, this is an electron that is created out of pure energy in the nucleus. It's not an orbital electron, right? The particle that's created is an anti-electron neutrino, electron neutrino, an anti-electron neutrino. There's many types of neutrinos. This is an electron neutrino, and it has to be an antimatter one so that it conserves something called lepton number. We're not going to actually get into particle physics, but there's something called lepton number. Electrons are leptons. There are other ones that are leptons, right? Electrons are the lightest one. But anyway, there's something that's conserved. We're not sure why this is, but if you create a matter one of these, you've got to create an antimatter one at the same time to conserve that number, right? And so when you create the matter one, you have to create the antimatter one. This is an antimatter electron, and that's why a regular matter electron neutrino is created in that thing. So that's how you would remember that, if you could remember it at all, other than just memorizing it. Yeah. Say it again.
Does the neutrino have anything to do with conserving the charge in the nucleus?
No, because they're not charged, right? And in fact, neutrino, this is a funny thing, right? Neutrino is Italian. It was hypothesized by Wolfgang Pauli, named by Enrico Fermi, who's an Italian scientist, and it just means in Italian, little neutral thing. Yeah? Yeah.
Can you explain antimatter for a second?
Yeah. Okay, antimatter is the same. It's like this. Everything has its dark side, right? Okay. So there's antimatter protons, right? Antimatter neutrons, antimatter electrons, right? And they all have the same. If the matter particle has a charge, the antimatter particle has the opposite charge, if it's charged, right? And then it has the same mass, exactly the same mass, and it has all these numbers like lepton number or whatever. Antimatter particles have negative that number.
How do you?
And generally, antimatter isn't around. We generate it in like particle accelerators. This is one of the exciting things you do with a particle accelerator, is make antimatter. It doesn't.
I heard that like one of those places, I forget what it's called, is like trying to like build up a certain amount of it.
Yeah, sure. Or make an atom, or make even something of it, right?
So what would that do if it like touched?
Well, if you had enough of it, obviously it would release a tremendous amount of energy, right?
In that Angels and Demons movie, they like were trying to like steal it so they could blow up the city.
Right. Yeah. Not likely that you'd have that much, but
Why is there a bar over one?
That means antimatter. The bar means antimatter. Okay, and then I think we've already talked about these guys here. Beta plus is a positron, right? We've already talked about this. Talked about that. This is Wolfgang Pauli. He was famous for the following statement. If he believed that somebody did not have a good argument and he did not want to argue with them, he would say that their argument wasn't even wrong. I kind of like that. I have yet to use this on anybody, but just the notion that I'm not going to consider that. It's just obviously wrong. It's not even wrong. It's not even couldn't even be considered right or wrong. It's out of the running. Okay. I like this. This is the story I've already told. He proposes it. This is Enrico Fermi, an Italian scientist who was in the United States. There's a lab in Chicago, I think, isn't it? Fermi Lab, named after him, a very famous nuclear physicist, right? Okay. In 1956, when they were confirmed, nobody was questioning their existence. They were mathematically confirmed using, I can't remember, they weren't directly detected in 1956. Here's the thing that directly detected neutrinos, okay? And it's called the Super K. It's inside a mountain in Japan. And that's because anything that could detect a neutrino would be so sensitive to background radiation, et cetera, from cosmic rays, solar radiation, that you have to hide it from all that, right? So here's the thing. Billions of neutrinos are streaming through your body right now, yes? They are not interacting with your matter. Some of them have traveled from the other side of the universe and are now just reaching you, yes? Okay, so neutrinos are very interesting things because light from the other edge of the galaxy interacts heavily with matter. And it's like clouds of gas and dust and stuff block light, but not neutrinos. So if we can build a telescope that uses neutrinos, we can see all the way to the other side of the galaxy, right? The other side of the universe, right? Okay? Yeah.